Hey, so yesterday we looked at landforms that you would find underneath the ground. Today, let's look at the stuff that are up here on the surface. First of all, hills and mountains. Pretty simple. You know what a hill or mountain is. But scientifically, what this means is you've got a chunk of land that is higher than the land around it, and it has a definite top. And you can see how these two pictures fit that definition. There's my definite top, and this is higher or raised up over the land around it. Same concept here. There's kind of the base level. There's my definite top, and here's my landform that is higher than the land around it. That's what a hill or mountain is. The question becomes, well, what's the difference between those two? So, well, scientifically, there is no difference. This is like the lake and the pond, where scientifically there was no difference, but most people want to call a lake or a pond, or a lake bigger than a pond. In years past, in prior times, people wanted to say a mountain was something that was over a certain height, whatever that number was. Well, now it's more assumed to be that, well, they're really the same. And if you want to call one a mountain or versus a hill, that's kind of more like a common term, not necessarily a scientific term. But hills and mountains have different tops. A crest is what we think of when we think about the top of a mountain. It's that one point at the top that is the absolute highest point on the hill or mountain. But if you look at the picture on the right, this follows the definition of what a hill or mountain is. Here I've got a chunk of land that is higher than the land around it, and it has a definite top to it, but the definite top isn't one point. That's what we call a ridge versus a crest. A crest is one point that is the absolute highest. A ridge is where you have a line or a continuous stretch of the landform that is all about the same height or the top. Now we want to sketch those. A crest is a nice point. A ridge is kind of like what you see there. You need to understand the difference between the two. Now let's talk about these landforms because they are related. They're cousins to one another. Plateaus, mesas, buttes, spires, and hoodoos. First of all, a plateau. A plateau is a big chunk of land. They're actually hard to get photographs of. In this case, if you're in a plane, you can see that that is a big chunk of land. That's really, really wide. It has a flat top, as you can see, and it has really steep sides. It has at least cliffs on some of its sides. That's what a plateau is. But what happens now is it rains on that land, and when the water falls off the side, it, of course, erodes and weathers the rock. So my plateau ends up getting a little bit smaller, and it will turn into a mesa. A mesa is not nearly as big as a plateau, but it still fits the same definition. It's got a flat top, and it has at least one steep side, usually cliffs on the side. But it's going to continue to rain, and weathering is going to continue to happen, and my mesa that is wider than it is tall, something like that, will continue to get smaller and will turn into a butte. A butte is the smaller or little brother of a mesa. Now it is taller than it is wide because erosion has eaten away the sides of my mesa and has now made it where it is skinnier, and therefore it is taller than it is wide, and that's what makes a butte. Well, erosion is going to keep happening, and eventually it's going to turn into something like this. A spire is a butte that's now so small that it has a pointy top to it. Draw something like this to get the idea of what a spire is. Now, a hoodoo. A hoodoo kind of fits the same definition. You see it here, we've got our flattened top and we've got steep sides. But what's different with the hoodoo is that it has very uneven sides. And what causes that with a hoodoo is you've got different types of rock in here. So they weather differently. You see the rock up here at the top must be tougher, because it's not shrinking, it's not weathering this way nearly as fast as that rock is. So a hoodoo has uneven thicknesses. Sometimes they call them a totem pole rock. And the reason why they have that shape is because you've got different types of rock that are weathering differently. Now, a natural arch versus a natural bridge. They both have the same general shape to them. There's an opening underneath. The difference between these two is that a natural arch was generally caused by wind, and a natural bridge was caused by water. Think about what bridges do. Bridges go over water. So that's how we're going to remember those being different. A natural arch caused by wind versus a bridge, which bridges tend to go over water. Now, canyons and valleys. Canyons and valleys are depressions, low points that go in one direction. And you can see here's my low point down here, and you can see they're all in a line. That is an example of a valley. A canyon is the same thing. It is a low point. See where my river is, and it goes somewhere. The difference between a canyon is it's got steep sides like cliffs. Valleys tend to be one of two shapes. They either tend to be U-shaped or they tend to be V-shaped. And we're not going to get too much in the weeds as to in which situation do you have one versus the other, but it is certainly influenced by how much erosion is taking place, which goes to, well, how much water is there? What's the type of rock that is being weathered and eroded? Just realize that valley is going to be one of those two shapes. All right, so here I am. I'm in a valley. Remember that a valley is a depression that goes in one direction. And you can see this narrow area behind me here that is going that way. It came from this direction and it went that way. Now, a little more specifically, this is definitely a canyon, because remember, a canyon is a valley with very steep sides, typically cliffs for sides. And you can tell here, this is a valley that has very, very steep sides to it. Even more specific, this is what's called a slot canyon. A slot canyon is a canyon, which remember is a valley that has cliffs for sides, but a slot canyon is one where it is significantly taller than it is wide. And you can see in this picture here how narrow this canyon actually is. This is very typical of a slot canyon, where they can be sometimes up to 1,000 feet high, but so skinny that you can touch each side. Now, these get to be very, very dangerous when it rains, because the water comes rushing in here, and you see there's no place for the water to go. This would be a place where you could very easily drown if you had a summer thunderstorm, because there's no place for you to get out of the way of the water that's coming in. So once again, this is called a slot canyon, which is a canyon that is significantly skinnier than it is tall. So let's take a look at this area around me. Notice it's kind of flat. I'm at the lowest point, and you'll notice all of these high mountains all the way around me, which means I'm in a low point surrounded by high points. I'm in what's called a basin. A basin is a low point that is entirely surrounded by higher elevation, kind of like a bowl. So let's move on to the rivers, because we know the water is the biggest agent of change in making these landforms. And we know that not all rivers are the same. Some move fast, some go slow, some got a lot of water, and some have very little water. So the characteristics of the river are going to affect what the land is shaped like. So think about these two here. Both these cases, we've got a lot of water and it's moving really fast. Well, why is the water moving really fast? Because there is a steep gradient. So if there's a steep gradient, the water in the river is going to move fast, and therefore it's going to cut through the ground pretty easily. However, here, see the water's just barely sitting there. It's not moving very fast because the ground is flat. That's a shallow gradient. This means the river moves slow and it can't cut through the ground very easily. So it's more likely to drop sediments, which then pile up and make the river change direction. Now, when a river's running fast, there are no sediments to drop because the water's moving so fast, it's going to move all of the sediments downstream. So let's talk about when the river moves so slow that it's picking up all this sediment and it can't carry it anymore, it's going to drop them. And sometimes those piles of dropped sediments get higher than the water. That is what's called a bar. You typically hear about this as being a sandbar, but it doesn't have to be just sand. It can be sand, silt, clay. It can even be other types of rocks. These piles of stuff can be in the middle of the channel. That's what we typically think of, just a regular old plain old bar. Or they can be on the side of the channel, kind of sticking out. And that's what we call a point bar, because it looks like it kind of comes to a point. Well, as the rivers start to turn and it hits those piles of sediment and makes the water kind of go off to the side, it means it hits one riverbank harder than the other. The water is hitting this side more directly, which means it's going to cause more erosion on that side than the other side. Because we know what it's doing over here. It's dropping sediments. Well, that side of the river where the water is hitting it harder and taking stuff away is called the cut bank. It is cutting into the bank. And cut banks are generally always opposite of point bars because all of these sediments here are making the water go that way more, which makes it hit that side more and cut into the opposite side. So this is going to happen more and more over time because as this point bar gets bigger, it's going to force more and more of the water to go to the other side, which is going to take away more and more stuff. So you get this pattern over and over again, and eventually the river looks something like this, where you get these big point bars, and the river just keeps getting cut more and more on this side, and more stuff gets dropped here, and you get a very unique shape to the river. You get these very wide sweeping turns. Those are called meanders. A meander are these really big, long, wide turns in a river. Now, eventually, especially if you get a really strong rain event and all of a sudden there's more water in the river, the water can actually break through that skinny point. It doesn't get hung up around the point bar anymore. It's going to go straight through. Well, once it starts going straight through, there's no reason for it to go over there, and you're going to get less water going that way, so more stuff is going to get dropped, and what you wind up with is this part of the river is now isolated. It's cut off. And that's what's called an oxbow lake. And you can see it here where this water was originally part of the river channel, but it's now been cut off because too much sediments have been dropped here and it blocks the water and the water just keeps going that direction. Now, where would you expect to find these oxbow lakes? Well, it's got to be a place where the water is going pretty slow. It's got to be across flat ground because remember, to make the water do that shape, you had to have a lot of sediments being dropped. Well, there aren't any oxbow lakes in the Chattahoochee River to speak of because here in the Chattahoochee, the river is running pretty straight, which means it runs pretty fast. However, if you go up and down the Mississippi River, where it's a big, wide, flat river, and it's carrying a lot of sediments, you get these oxbow lakes being formed all the time. Here you can see some satellite images. They are all up and down the Mississippi River. Now, speaking of sediments, we know that sediments get dropped alongside the river when you get a flood. And there's something like this. Here, the water comes out of the river, and it drops the sediments right beside the river, and we wind up with a pile of those sediments. You get these little hills right beside the river called levees. And we have them in our area. Here I have a big creek, and you can see the creek. It's got all that sediment in there. I'm standing right beside the creek. But as I pan to the right, you'll notice that the rest of the ground over here is lower. So there's this little hill right beside the river, or right beside the creek, and that's what a levee is. You can see the water there. The water came out of the creek, it piled it up right there beside the creek first. That's what a levee is. And these can be very, very useful for us.
So levees start off as a pile of sediments or a little hill that goes alongside a riverbank when the river floods and drops sediments right alongside. Now, if we take these levees and we make them taller or we make them continuous, they can actually help to prevent flooding because then the water, when it gets high, can't come out of the river and therefore can't go over there and flood our town. So this is what we've actually done with levees is even though they started off natural, we've made them bigger, taller, and stronger, and now they help to prevent flooding.
They're natural and they're found alongside a lot of rivers. They're found in all 50 states. And we use these levees now to help keep water in a channel and prevent flooding. In South Florida, there's this huge system of levees that keep the Everglades water in the Everglades. You can actually see it on a satellite image. Over here is Miami. And you can see over here where it looks wet because as the water moves across the southern part of Florida, they have built up these levees extra higher to keep the excess water out of Miami and keep it in the Everglades. Now, there's some good and bad to this, though. One, yeah, it's great. They help keep water in the river, which therefore prevents flooding. Great. But remember, this is something we have done. We have changed the course of nature, and they prevent new sediments from being deposited in the floodplains. So, especially with farmland, where you necessarily need some new sediments to help keep your soil good, these levees aren't doing you any favors. Now, where else does the river drop sediments? Well, when it gets to the ocean. We know that when rivers get to the ocean, they stop and they drop sediments because the velocity of the water goes to almost zero. Well, the sediments pile up. Well, the water's still got to get to the ocean, so it ends up going around the pile of sediments. And what you wind up with is a triangular shape of land called a delta. And it comes from the Greek letter delta, which is a triangle. So this rock right here is a little bit different than that rock up there. You can kind of see a difference in the color. Well, as it turns out, this rock here is a lot more easily weathered or broken down than the rock up top. So now when the water from this stream comes down here, it's able to weather away and take away the rock on the bottom because it's softer. The rock at the top is a lot tougher and more resistant to weathering. So we get this uneven weathering, we get differential weathering. And that's how a waterfall is formed, when you get harder rock over softer rock and they weather at different rates. Well, let's look at the landforms we have along the coast. First of all, we get this definition, a headland. I got this big chunk of land that's sticking out into the ocean. And it gets hit by the ocean, tides coming in and out, and it will make a hole in the bottom of it, and then we get a sea cave. Well, if the water goes all the way through, we get a sea arch. And eventually the arch falls down and we get a sea stack.
So let's examine the formation of sea stacks like the one you see here behind me. What you have to start off with is a headland. You've got a piece of land that's sticking out here into the water that has cliffs all the way around it. Well, the tides and the waves come in every day, and you can see that as the water hits the bottom of the cliff, it slowly starts to eat away the rock down here at the bottom. And if this is a headland that is sticking out into the ocean, it's going to do it from both sides. Well, eventually what happens is, down here at the bottom, the water is able to eat through the rock or eat through the headland on both sides, and you wind up with a little opening there that the water can go through. That would then be a sea arch. And this, you can kind of see the circular shape. It started off as a sea arch, but eventually too much of the rock gets eroded and taken away that it can't support the weight of the arch anymore. The arch falls down, and now what you have is a sea stack.
Here you can see a couple of them. We've got the headland, we got a sea cave, sea arch, and we've got a sea stack all in the same picture. Now, barrier islands. Barrier islands are small sandy islands, usually parallel to the coast, where the action of the wave starts piling up all of the sand into these long, skinny islands. And you can see them in this picture. You can actually see the sand being moved around. And they're very common along Florida. They're very common along the Gulf of Mexico. You can see these long, skinny islands in these satellite images. This is Fort Myers. You also see it along the North Carolina coast, all along the Gulf Coast of Alabama, Mississippi, Louisiana. The whole coastline of Georgia is nothing but a chain of barrier islands, one right after another. So the question becomes, why do we have so many barrier islands all along the Gulf Coast in Georgia? Well, that's because we got a lot of rivers, and we rain a lot here. So all of these rivers keep going to the coast and they keep bringing sediments. And when the sediments get to the coast, they get dropped and they pile up and they make these huge piles of sand right along the coast, parallel to the coast, and that's what gives us barrier islands. Now let's look at California. Notice there aren't any barrier islands along the coast of California, and the difference with California is they don't have a lot of rivers bringing sediments to the coast because it doesn't rain very much there. So very distinctly different shapes to the coastlines in the east, where we have barrier islands, versus in the west where we don't. Now let's look at some glacial landforms. We get glaciers, rivers of ice, very heavy, just bulldozing their way through the land, and they cause some very, very unique shapes to the land.
So what we've got here is a valley. Remember that a valley is a low point that goes in one direction. This valley could almost really be called a canyon because we can see the sides of this valley are really, really steep. They're almost cliffs. Now what's different about this valley is how it was formed. Most valleys are caused by rivers that as they flow, they move rock and material, dirt out of the way and make that low point. What's different here is that this valley was caused not by flowing water. That's not a river back there. This valley was caused by a glacier. 10,000 years ago, there was a huge chunk of ice coming out of those mountains, and it moved this way, and it pushed all of this rock and dirt and soil and material all out that direction. Well, what's out there is the ocean. Like most rivers, they flow to the ocean, so do most glaciers. So this glacier pushed itself all the way to the ocean. The glacier's not here anymore. It melted after the last ice age. So what has come up this valley is salt water from the ocean. This is not a river. This is actually part of the ocean. And what we have is a very deep canyon that pushes to the ocean. That is a special type of landform, and it's called a fjord. A fjord is a deep valley or canyon that goes to the ocean that was formed by a glacier.
So where would these fjords be found? Well, you got to be pretty cold because you got to have the glaciers. So we don't have any fjords in Georgia. As a matter of fact, the word fjord is from the Norse language or Norwegian language because that was the place that first gave that specific name because that's where they are found. You will also find them in Alaska and in Iceland.
So let's take a look at the way this land is shaped right back here. This is a special type of landform, and it was caused by a glacier. And you can see there's a lot of snow over there. Now this isn't a glacier anymore, but thousands of years ago during the last ice age, there was a tremendous amount of snow and ice. There was a glacier that was flowing. It was moving into this part of the water. Well, all of that glacial pressure picked up and moved and bulldozed a bunch of that rock out of the way. And now what we see is we have this kind of cup shape, this circular shape, where the glacier has changed the shape of a land. That particular shape of land caused by a glacier is called a cirque. A cirque is a French word, and it means circle because you can see this is a circular depression that was caused by a glacier.
Now, if you get a bunch of cirques side by side, there was one, there was one, there was one, there was one. What you wind up with is the little row of land in between. And you get a very thin ridge of rock between those, and those are called arêtes, which is a French word because these were first observed in the French Alps. But remember, you can have a tributary glacier that comes into a main glacier. So in this case here, we had a big, huge glacier right here. And over here, we had a side glacier, and they met. Well, the glaciers went away. And now what we have is this weird shaped valley that all of a sudden just ends as a cliff because that's where the glacier met the bigger one. And that's called a hanging valley. A hanging valley is where you've got the side glacier valley, even though the glacier's not there anymore, and you typically have a very, very steep drop. Had that valley been formed by a river as opposed to a glacier, it wouldn't have this waterfall. It would have cut a more direct single gradient path.
So back there's my glacier, and we know a glacier's water, and water as it moves stuff. Well, a glacier moves lots of rocks and sand and soil, and when it gets to the end, when the glacier ends, it can't move the stuff anymore, so it just drops it. That stuff is called till, and you find big piles of that stuff at the end or beside glaciers. Those are called moraines. A moraine is a pile of till that is made by a glacier.
It can be at the end or they can be beside. And sometimes these piles of stuff, this piles of these moraines, can be so big that they're given their own name. Specifically in our country, Long Island, New York, and Cape Cod, Massachusetts are simply moraines from the last ice age. And these are big landforms. Lots of people live there because that's how big the glaciers were and how much stuff they moved.
So look at these little scratches or grooves in this rock. These were caused by a glacier about 10,000 years ago. And when you had all of that ice moving forward and backward over this rock, and it had little rocks in the bottom of it, those little rocks under the weight of the ice dug into the exposed bedrock and left these little scratches. These little scratches are called striations. Striations are grooves or cuts into rock caused when a glacier moves back and or forth over it. So because glaciers are so large, they can be very powerful and make really big and deep cuts in the ground. And that's what we see back here. This is in Maine, where during the last ice age, a glacier moved along here and made a big, huge carve into the ground. And it rains a lot here, so it filled up with water. So these glacial striations can lead to the formation of some very uniquely shaped, some long, skinny, and deep lakes.
That's like the Finger Lakes in upstate New York. Notice they're all kind of pointing the same direction. There are long, skinny striations that are now lakes.
So glaciers were moving back and forth over this area, and the glaciers were picking up rocks and sand and dirt and stuff and carrying it over long distances. And when the glaciers retreated, they melted, they dropped that stuff in place and gave us a very uniquely shaped landforms. And this is one of them. This is called a drumlin. A drumlin is a long, skinny, teardrop-shaped hill that is formed when a glacier retreats and drops its stuff.
You can see them all up in the Northeast and even in the Midwest. You can see all these little drumlins, and you can see how they're all aligned the same direction because that was the way the glacier was moving. And this is how we know which direction the glacier was moving. You can all see them. Glacier must have been going back and forth this way because that's the way these drumlins are oriented. Now, where do we expect to find all these things I just told you? Well, it's up there where the glaciers were during the last ice age. So once again, we're going to say upper Midwest and the Northeast. So here's Georgia's glacial landforms. And yes, I know it's a blank page because there were no glaciers that have ever come this far south. We don't see any of those glacial landforms. Now, volcanoes and the remnants of volcanoes can also make land shaped a particular way.
The depression that you see in this picture or in this video in front of you is called the caldera of a volcano. Caldera, spelled C-A-L-D-E-R-A. And the caldera is the depression formed at the top of a volcano once the eruption is over and the ground kind of collapses on itself because the volcano is no longer pushing material out its top. Now, this is Kilauea volcano in Hawaii, and that deep pit out there was about 280 feet deep before the eruption of 2018. And they had a huge eruption in 2018, and a lot of the magma came out of the volcano, and so it ran out of gas, so it's not very full anymore. And that caldera collapsed to a depth of about 1,600 feet, so the land just sank down after the eruption was over. So once again, this is a caldera, or the depression in the top of a volcano that's left over after the eruption ends. So what we've got back here is some old magma. We've got some melted rock from deep inside the earth that was trying to get to the surface, and it couldn't make it, and it got stuck. And when it got stuck, it hardened into this solid volcanic rock. And remember from our study of rocks that igneous rocks that form under the ground are a lot tougher than the ones that make it to the surface. So Here we've got this volcanic formation, and this is part of a general classification of volcanic landforms called plutons. A pluton is a chunk of magma that hardened under the ground that is now above the ground. More specifically, this is what's called a dike, D-I-K-E. A dike is a vertical pluton as opposed to a horizontal one. And you can see this was obviously vertical. There was magma that was trying to go to the surface, and it got hung up, it got stuck, and it hardened. So why is this above the ground now? Well, millions of years later, all of the softer rock over this has been weathered and eroded away. This is really, really tough rock because it hardened underneath the ground, and this is what we see left over. So once again, a pluton, that is a volcanic landform that is the result of magma that formed under the ground that is now above the ground. More specifically, this one here is a dike, D-I-K-E. A dike is a vertical pluton.
Now, sometimes you can have these really big, huge plutons, like a whole mountain range. That's called a batholith. That is a large pluton. That is a huge chunk of magma that hardened underneath the ground that is now above the ground. You can also have laccoliths. Laccoliths are a little bit smaller, like a single mountain. And all of these here are classified as what's called exfoliation domes, where you have like a bubble of magma that is now above the surface. Stone Mountain is a very famous example in our area of an exfoliation dome. Now, volcanic plug. Volcanic plugs are the remnants of an old volcano. This was where the last bit of the magma from the volcano was erupting, but it stayed inside the volcano, and it hardened, and it basically formed a dike. But over millions of years, all of the soft stuff has now eroded, and only the tough stuff is left behind. And they make very dramatic landforms like Shiprock, New Mexico, which was a very famous landmark on the trails going west by the pioneers. They didn't have maps. They looked for that landforms. Oh, I go to that very unique looking rock and keep going. Devil's Tower in Wyoming, same thing. And Morro Rock in California. These are all examples of volcanic plugs.